Hello everyone. Today let's learn about binary search algorithm by solving this particular question. So given a sorted array, search if k is present or not. So we have an array of 10 elements and we are asked to find if a particular element is present in this array or not. If the element is present, let's return true, and if it is not present, we have to return false. It's a very simple question, and let's think about the different approaches that we can use to solve this particular problem. So one of the brute force methods that we can implement on this particular problem is like we can just use a normal for loop and just iterate over all the elements, and we can check if that element is present inside or not, and we can return true if the element is present. So for example, okay, so idea one is to search over all the elements and check if the element is present or not. And for that, the worst case time complexity will be big of n, right? Because we go through all the elements, right? And another method that we can use to solve this particular question can be using a hash map. Maybe we can put all the elements in a hash map and run a search. But in that case also, what happens is if that is idea 2, the time complexity will be again of n itself. And again, in this case, space complexity will be big of n because we are using a hash map. And in this, the idea 1, the space complexity will be big of 1 because we are not using any extra space, right? So yeah, a linear time complexity is good, but can we do better? That's the question. So that is where binary search comes, and let's see how efficient binary search and why binary search is efficient than time complexity of n, right? So basically, how is binary search working? So let's take the example of a dictionary. If you are searching for a meaning of a word, for example, if you are searching for a word energy, and we know energy starts with E, we randomly open a page in a dictionary, and suppose we land on a page that starts with P, words that start with P. Okay, we know E comes before P, so we don't have to check the rest of the dictionary, right, which comes after P. We just check the pages which comes before P, and we just again randomly open a page which comes before P, and we land on a page which starts with the letter C. Okay, now we know E comes after C, so we don't have to check the the left side or the letters that comes before C. So we go to the right part, which are the letters that comes after C. So binary search also works in a similar manner. Let's see how it is done. So let's take the same elements, all right, and we know this is sorted, right? Yeah. So we have 3, 6, 9, 12, 14, 19, 20, 23, 25, and 27, right? So if this is the array, and what we initially do is, let's instead of randomly checking any element, let's go and land on the middle element, right? So in this case, we are checking for if k equal to 12. 12 is present in this array or not. And for example, let the middle element be 14. Okay, so we selected the middle element and we landed on 14, and we check. We need to check for 12. So we know 12 is less than 14. So what is the conclusion from this? If 12 is less than 14, we don't have to check any elements that is to the right side of 14, because every element that is, because this is a sorted array, every element that is to the right of 14 will be greater than 14, and every element that is greater than 14 will definitely be greater than 12. So 12 lies somewhere in this area, right? Somewhere in the left part, right? So what happens is, if we land on an element that is greater than 12, we one second, let me change the color. We just search for that part, which is this, and we can just ignore the other part. We don't have to search for any elements that is on the right side. We just have to search the left side, right? Because 12, the element that we're searching for, is less than the middle element, right? So let's again, this is case 1. Okay, we take the middle element, and the middle element is greater than the number that we are looking for. So now comes the case 2. Sorry. So we land on the middle element, and suppose the middle element is 9, for example. Okay, if the middle element that we got is 9, and we check the number that we have to search for is 12. Is 12 is greater than 9. 12 is greater than 9 means 12 will lie somewhere here, right? Now every element to the left side of 9 is less than 12, 9, so it will definitely be less than 12 also. So 12 lies somewhere here. So we can discard this particular portion and only search for the green area, that is to the right side of 9, right? Let's take the marker. Yeah. Now we only have to search for the right side, that is this side. Okay, this is a bit more thick. Okay, in this case we check the left part because 12 is less than 14, or the element that we got in the middle. In this case 12 is greater than the middle element, so we just have to search the right part, right? So if we get this condition, what happens? One second. So in case 1, if we get the element that we are searching for is less than the middle element, so the condition being that, then we go to left, and if the element that we are searching for is greater than the middle element, then go to right, search for this part. Okay, here search for this part, and then comes the third case, that is we just check exactly the middle element, and by luck this time the middle element is exactly equal to the number we are searching for, which is 12 itself, right? And what should we do when the middle element is exactly equal to the number that we are searching for? We just have to return true, right? Nothing else. This means that the number is present inside it and we have found it, so we just return true. When it is greater than the middle number, then go to the right part, and when it is less than the middle number, then go to the left part. That is what we are doing in these 3 cases. So these 3 cases exist in when we are using binary search. Now let's elaborate and check with the example, and let's see how to implement in this in code, right? Let's write the pseudo code and let's do a dry run and let's see how it works. Okay, so we have the array with the numbers and with their respective index, right? Starting from 0th index up till 9, and we have 10 elements, right? So the first thing that we have to do is set 2 pointers, low or high. For this case I'm using left and right, and I'm setting the left index at the first index, that is the 0th index, and I'm going to set, okay, let's change the color for now. The left index will be at 0 and the right index will be at the last element, which is 9 in this case, right? And to find the middle element, what we have to do is we just have to add these left and right elements and divide it by 2. For in this case the middle element will be L plus R by 2, which is equal to 0 plus 9 by 2, which is equal to 4.5, and we take the floor value, so this is equal to 4, right? And 4 means the 4th index, this is the middle value. Okay, so ARR of 4 is 14. 14 is the middle value in this particular array. So let's do a dry run here. So here is L, here is R, and here is the mid value, which is equal to L plus R divided by 2, right? So initially L is 0, R is 9, and mid equal to 4, right? 4 means the index, so ARR of 4, that element is 14, right? So we know what the element that we are searching for, which is k is equal to 12. We have to search if 12 is present in this or not. So we know 12 is what? 12 is lesser than 14, which means go to, let's erase these things. Yep. Okay. Yeah, so 12 is less than 14, which means 12 will lie somewhere on the left side of 14, right? So we can discard the whole right side of this. So I just have to check this particular array. Now the array becomes this one, right? Not that. Okay, now the array becomes this. We know 14 is not that, not the element. So now the search area is reduced to the left part, this one, right? Go to left. Now what do you mean by go to left? Going to left means the position of L remains same, which is 0 itself, and the right index will come and will reach here, which is 3, right? Now the array becomes this, which is 3, 6, 9 and 12. Index 0, 1, 2 and 3, which is L is here and R is at the third index, right? So what happened here is like the value of L didn't change. L is remaining the same itself, so we don't have to change that. L is at 0 itself. Only thing happened is when we are going to write, the value of R changed. Now what is the value of R? R is the value of R, which is 3. That is just one element or one value less than the middle element, which is the initial mid value, which is this was mid initially, and now in this case R is R equal to mid minus 1, right? So when R is mid minus 1, the value here changes. Mid was 4 initially, 4 minus 1 is 3, so value of R changed to 3. Now we need to find the new mid. The new mid is like L plus R by 2, which is 0 plus 3 by 2, which is 1.5, and the floor value is 1. So it becomes ARR of 1. And let's see ARR of 1. The first element is 6, right? Okay, right. So 1 equal to 6. We know 12 is greater than 6, which means what? 12 lies somewhere to the right side of 6. We need to go to this side, right? So go to right. Now what do you mean by going to right? When we go to right, what happens is the value of R, the index at where R is, remains the same, and we need to change the index of L, or position of L, right? So now L is going to this. Now the new array becomes this. We only have to search the area that is to the right side of R, which is this one, right? And R the right side of 6, and now R is at the third index and L needs to be shifted to this particular index, right? Now L equal to 2, which means L is shifted to one index greater than the original mid value, which is L is equal to mid plus 1. In this case mid was 1, 1 plus 1 equal to 2. So the new mid will be 1 plus 1, 1 plus 1, which is so the new L value will be mid plus 1, that is 1 plus 1 equal to 2, and R remains the same, which is at 3 itself, R equal to 3. So the new mid value will be 2 plus 3 by 2, which is 2.5, and the floor value is 2. So ARR of 2 is the new mid value. Let's see ARR of 2. ARR of 2 is 9, right? ARR of 2 is 9. So 9 is what? 9 is less than, sorry, the value we're checking for is the value we are checking for, sorry for the background noise, the value we are checking for is 12, which is greater than 9, which means we need to only check for the right part of 9, that is towards the right. 12 only lies towards the right part of 9. That means again go to right. Go to right means L becomes mid plus 1 and R remains the same. So now what is mid? Now mid is 2, mid plus 1 will be 3. Now the new L and R values will be L equal to mid plus 1, which is equal to 2 plus 1, which is equal to 3, and R remains the same, 3 itself, and the new mid is equal to 3 plus 3, 3 plus 3 by 2, which is 2.5 again, sorry 1.5 again, sorry 3 itself. The new mid is 3 plus 3 by 2, which is 3, and ARR of 3, which is equal to what? ARR of 3 means it comes to this point, that is, let me just write it down again. just one element that is at the index 3, and now both L and R is at 3 itself, and that element is 12, and we got it. Like when L and R are on the both L and R both are equal, we landed on the element 12, and we can set a condition that when L and R are equal, then just break the loop, and we got 12, which is equal to mid, in this case mid value is equal to the value that we are searching for, which is k, that is 12, and in that case we need to return true and break out of the loop. That is what is happening here. Now let's see the pseudo code for this particular problem, right? So what happens initially is so let's write a function, maybe search, and we'll be given an array, an integer array. So and then we'll be given the element that needs to be searched for, which is k, right? And we need to return a boolean value, which is true or false, so the return type will be boolean, right? And what else? We are going to set the L value. Initially the L value will be the first index only, or the 0th index, the initial index, which is 0, and the R is going to be at the last index, which is length of ARR minus 1, right? Which is because if there are 10 elements, the last index will be 9, so when we check the length, we'll get 10, so we'll reduce minus 1 from that, so we'll get 9, right? What else? Yeah, so we need to set the value of mid, right? So mid will be equal to L plus R whole divided by 2. Fine. All right. So what? We have 3 cases. So yeah, let's write. So first case, if so if the mid value that we selected is exactly equal to what we are searching for, right, is equal to k, is equal to k, then what should we do? We should just return true, right? That is sorted. So else if what? Else if the mid value is less than k, what happens? Which means the mid value is 14, right? For example, if the mid value that we got is 14 and the element that we are searching for is 12, and the mid value is lesser than 12, which means we need to go to the right part, right? Which means go to right. And what do you mean by going to right? Going to right means we need to set R as that index itself, and we are shifting L. For example, here is it. Let's take another example. 1, 2, 3, 7, 6, 9, 12, 20, 21. So if this is the array and we're searching for 12, and the mid value that we got is 6 in this case, all right? So mid is less than 12. So we need to ignore this part and go to right. Going to right, okay? So initially L was this. Let's add the index also. 0, 1, 2, 3, 4, 5, 6, 7, right? So initially L was at 0th index, and R was at the index 7, and the mid value that we got is 6, that is less than 12, and so it is less than 12. We need to go to the right part. Going to right part means we need to shift L to the element that is next to the mid, which is this, right? That is L equal to mid plus 1, and R remains as it is. So what happens is just change the code like this. Going to right means we are what are we doing? We update the value of L equal to mid plus 1. Whatever was the value of mid initially, increase the value of mid to 1, and that is the new position at where L should be, right? So close that. And if these both are not the case, if mid is not equal to k and if mid is not less than k, then the only remaining case will be mid is greater than k. So else, what should we do? else we should update the value of r. So for example, the mid value is 20, right? We don't have to go to this part, we just have to search for the left part, right? So what happens is we just update the value of r. We push r to this value, and l is wherever l it is. L was initially here, right? So L remains the same, and we push the value of r to this particular index, that is 1 less than the original mid index. So we update the value of r here. R becomes r equal to mid minus 1, right? Now we need to do all these things while there is a condition, that is while the L value is less than or equal to r, do all these kind of things, that is up until this, right? And we run the whole loop, and if the element is not present in that, we need to return false, right? Return false. And we have the code, right? Everything is perfect on this. Everything is sorted on this. Now we still have a question remaining. Why is binary search more efficient than a normal iteration which involves a time complexity of n? So here is the answer for that. So every time, suppose we have n elements, right? So every time we are discarding n by 2 portion of the elements, and we are searching for only the half portion of that. So initially we are searching for n by 2 elements, then we are searching for that is divided into 2, n by 4 elements, then we are searching for n by 8 elements, so on, which means every time we are searching for n by 2 raised to 1, n by 2 square, n by 2 cube, etc., which means until there is just one element, which becomes n by 2 raised to maybe k equal to 1, which is n equal to 2 raised to k, that is k will become log n. So which means the time complexity in this case is log n rather than n, the linear complexity that we use in normal iterations, and log n is always less than n, and hence we have a better time complexity, that is log n in this case. So the time complexity when we use binary search is big O of log n, and hence binary search is preferred in these situations rather than a normal linear time complexity. Yeah, so that is about binary search, and this is like a level 1 or 2 difficulty level question in binary search. We'll be back with more questions with varying difficulties, more difficult questions in the upcoming videos. Stay tuned for that, and if you if this video was helpful for you, just like the video, and yeah, bye for this time.